Hello friends, today's lecture we're going to talk about pile foundations. Chapter 9. What is a pile in foundation engineering? Let me define. Piles are structural members that are made of steel, concrete, or timber. They are used to build pile foundations, which are deep and which cost more than shallow foundations, of course. Sometimes it's called deep foundations in general instead of pile foundation. Despite the cost, the use of piles often is necessary to ensure structural safety. Some of the conditions that require pile foundations can be summarized as below. When surface soil layers are highly compressible and too weak to support the building loads, piles are used to transmit the load to underlying bedrock or a stronger soil layer. As shown in the figure, suppose that upper stratum or upper layer is compressible and or weak or any kind of problematic soil. So we have to transmit our load to strong layer. But when this strong layer, this may be a rock layer or a firm soil, hard soil, when such a stratum, such a layer is not observed at a reasonable depth. In this case, we can construct our pile foundation as frictional piles. In Turkish, sürtünme kazı, frictional piles. Such a pile gets its capacity from frictional resistance along the interface between pile and the soil. And of course, it can get some amount of end bearing, but generally it's negligible compared to shaft resistance. So these kind of foundations are called frictional piles. Second reason is when subjected to horizontal forces. Pile foundation resists by bending while still supporting the vertical load of the superstructure. We have still structural load, vertical load, but sometimes this pile foundation may be subject to lateral loads. This type of situation is generally encountered in the design and construction of earth-retaining structures and foundations of tall structures that are subjected to high wind or earthquake forces, lateral forces. Third case may be in swelling soils or collapsible soils. When expansive and or collapsible soils is present at the side of proposed foundation, proposed structure, these soils may extend to great depth below the ground surface. So, because the bearing capacity is extremely low, our load of superstructure should be transferred to stable soil below that by using pile foundation. The foundations of some structures, such as transmission towers, offshore platforms, or petroleum or natural gas, and basement mats below the water table are subjected to uplift force, as shown in this figure. For example, this is a high tower, high antenna tower, or maybe transmission tower. Due to wind loads or any lateral load, one side of the foundation is under compression, but the other side may be in tension. So, to support these tensional forces, pile foundations are used to resist this kind of uplift forces. Fifth reason is bridge abutments. Bridge abutments and piers are usually constructed over pile foundations to avoid the loss of bearing capacity that a shallow foundation might suffer because of soil erosion at the ground surface. In such a case, pile foundations are needed. For example, in these two figures, actually the middle one is picture possible score erosion is avoided, or effects of erosion is avoided by using pile foundations. These are top portion of pile foundations combined with a layer. Let us talk about types of piles. Piles may be made of steel, and geometry may be pipe or H-section. Pipe piles can be driven into ground with their ends open or closed. When necessary, steel piles are spliced by welding or by riveting, such as shown in this figure. The figure B shows welding, and the figure C shows riveting. When hard driving conditions are expected, such as driving through dense gravel, shale, or soft rock, steel piles can be fitted with driving point or shoes, such as shown in figure D and E. And these shoes or ends may be welded. Sometimes they're not welded. Steel piles may be subject to erosion. Soils that have a pH greater than 7 are not so corrosive. Factory applied epoxy coating on piles work satisfactorily against erosion. Here are some general facts about steel piles. Length of steel piles range between 15 to 60 meters, and usual loads range between 300 to 1,200 kilonewtons. Of course, we have some advantages and disadvantages using steel-made piles. Advantages may be easy to handle with respect to cutoff and extension to the desired lengths. Extension may be by means of welding or riveting, and can stand high driving stresses. We can use any driving hammer. Can penetrate hard layers such as dense gravel and soft rock, and high load carrying capacity. Disadvantages may be cost and relatively high cost compared to others, because steel is expensive material. High level of noise during pile driving, subject to corrosion. H piles may be damaged by deflected from the vertical during driving through hard layers or past major obstructions. These are disadvantages. Let us talk about concrete piles. They are precast piles actually, or in other words, cast in situ piles. Precast piles can be prepared by using ordinary reinforcement, and they can be square or octagonal in cross section. Reinforcement is provided to enable the pile to resist the bending moment developed during pickup and transportation. The vertical load and the bending moment caused by a lateral load. The piles are cast to desired lengths and cured before being transported to the site. Some general facts about concrete piles maybe. Their lengths range between 10 to 15 meters and loads 300 to 3000 kilonewton. They can be subjected to hard driving. This is one of the advantages. The others may be corrosion resistance because we use concrete. Can be easily combined with a concrete foundation, concrete superstructure. Disadvantages may be difficult to achieve proper cutoff, and length should be known before production. It's very hard to cut to desired length, and of course difficult to transport. These are disadvantages. The other variety of pile foundation is cast in situ or cast in place piles. They are built by making a hole in the ground and then filling it with concrete. These piles may be divided into two broad categories, cased and uncased. Both types may have a pedestal at the bottom as shown, pedestals as shown in these figures. Case piles are made of by driving a steel casing into the ground with the help of a mandrel placed inside the casing. When the pile reaches the proper depth, the mandrel is withdrawn and the casing is filled with concrete. Some general facts about cased and cast in place, cast in situ piles. Usual lengths range between 5 to 15. It may be 30 to 40 meters sometimes. Usual length 200 to 500 kilonewton. The maximum load is 800 kilonewton. They are relatively cheap compared to steel piles, especially. Allow for inspection before pouring concrete, and easy to extend. You can extend borehole to extend length of the pile. These are advantages. Difficult to splice after concreting, and thin casing may be damaged during driving. These are the disadvantages. One more variety may be timber piles, but timber piles rarely use today's technology because other types are easily made. Timber piles are tree trunks that have their branches and bark carefully trimmed off. So it's a natural material and used almost as it is. Timber piles cannot withstand hard driving stresses. Therefore, the pile capacity is generally limited by driving capacity. Steel shoes may be used to avoid damage at the pile tip. The tops of timber piles may also be damaged during the driving operation, so crushing of the wooden fibers caused by the impact of the hammer is referred to as brooming. To avoid damage to the top of the pile, brooming, a metal band or a metal cap, which is placed on top of the timber pile, may be used. Sometimes we use materials combined to get a composite material. So these type of piles are called composite piles. The upper and lower portions of composite piles are made of different materials. For example, composite piles may be made of steel and concrete. Steel and concrete, as shown in the figure, the upper portion is concrete and the lower portion is steel. And concrete and timber, as shown in the below figure, timber piles followed by concrete pile. Steel and concrete piles consist of a lower portion of steel and upper portion of cast-in-place concrete. This type of piles are used when the length of the pile required for adequate bearing exceeds the capacity of simple cast-in-place concrete piles. Timber and concrete piles usually consist of lower portion timber below the permanent water table and an upper portion of concrete, in any case forming proper joints between two dissimilar materials, whether in timber and concrete or steel and concrete, is very important and also difficult. So composite piles are rarely used when it is needed extremely hard to joint reason. One other variety is also popular in Turkey, continuous flight auger, CFA piles. CFA piles are constructed by using continuous flight augers. Continuous flight augers. What's continuous flight augers? For example, the complete section of a continuous flight auger is shown in the second stage. And by drilling to the final depth in one continuous process, we are drilling all of the borehole in one step, and then concrete again in one step. After drilling with continuous flight auger, and the second step shows this time borehole is completed, then the auger is gradually withdrawn, taken to the surface, as concrete is pumped into the hole through the hollow center of auger. Through the hollow center of auger. We are withdrawing the auger. At the same time, we are pumping concrete. So the remaining portion of the borehole is filled by concrete. We can use reinforcement if needed, of course, but generally used can be placed in CFA piles immediately after the withdrawal of the auger or immediately after the filling of concrete. We are pushing the reinforcement inside the fresh concrete. But generally, the reinforcement is limited by 10 to 15 meters, or I'm sorry, in two-thirds of the total length, and total lengths are limited by 15 meters. In general, CFA piles are usually 30 to 90 centimeters in diameter, with a final length up to about 30 meters. The following is a list of advantages and disadvantages of CFA piles. Noise and vibration during construction are minimized because we are not hammering. We are just drilling and concreting. The noise comes from only engine of these machines, or maybe concrete pump, and eliminates splicing and cutoff because we are making the hole and the concrete in desired length. These two are advantages. Structural integrity is less reliable, and soil spoils need the collection and disposal. For example, shown here, which comes from the side of the this auger. This should be collected and removed from the site. These two are disadvantages. What should be the length of the pile? Of course, this depends on the soil property. As a geotechnical engineer or civil engineer, we have to calculate this. How can we calculate pile length? How can we estimate pile length? Before this estimation, let us mention where the total pile capacity, QU, ultimate pile capacity, comes from. Actually, this capacity comes from resistance along shaft or along interface between concrete and soil and end bearing. So, considering pile capacity or components of pile capacity, we can categorize piles into two: point-bearing piles and friction piles. For example, when we have a strong layer, such as strong rock or dense soil, stiff soil, and almost all of the capacity of this pile comes from end bearing. And frictional resistance is almost zero. Why? Because to get frictional resistance, this pile should be mobilized downwards. But strong layer doesn't allow this mobilization. So almost all of the loads, all of the capacity is resisted by rock layer. This kind of piles are called point-bearing piles. Sometimes point-bearing may be due to penetration into strong layer at some depth. So again, ultimate capacity comes from end bearing or point bearing. In this case, we have some amount of frictional resistance, but it's negligible compared to point bearing, end bearing. Sometimes we don't have any strong layer to get support from the end of the piles. In such a case, point bearing is negligible compared to shaft resistance. Due to what? Due to small diameter. The shaft area, side area, is very large, so capacity, pile capacity, comes from this shaft resistance. And this kind of piles are called frictional piles. In Turkish, sürtünme kazığı, or in practice, yüzer kazık. Let us go into detail. Let us start with point-bearing piles. If there's a bedrock within a reasonable depth, piles can be extended to the rock surface. In this case, the ultimate capacity of the piles depends entirely on the load-bearing capacity of the underlying material. Thus, the piles are called point-bearing piles. If instead of bedrock, a fairly compact and hard stratum of soil is encountered at a reasonable depth again, piles can be extended a few meters into the hard stratum. In practice, this kind of piles are called socketed piles. In such a case, ultimate pile load may be expressed as Qu, ultimate load capacity of a pile, Qp plus Qs. Qp, load carried at the pile point, and Qs, load carried by skim friction developed at the site. If Qs is very small, what does it mean very small? Negligible compared to Qp. So we can assume Qu almost equal to Qp. In such a case of very strong soil, for example, larger diameter gravel. When no layer of rock or rock-like material, hard stratum, is present at a reasonable depth at a site, piles are driven through the softer material. The ultimate load of these piles may be expressed again in general term Qu, of course, Qp plus Qs. However, in this case, Qp is small, relatively small. Then we can assume ultimate capacity almost equal to Qs. These piles are called frictional or friction piles because most of the resistance is derived from skim friction. Actually, friction is applicable for sandy soils, granular soils. In such a case of clay soils, the side friction, shaft friction, comes from adhesion on this interface. But in general, whether this soil is sandy or clay, we use friction term, frictional pile. But we know in clay soil it comes from adhesion along this interface. The length of friction piles depend on the shear strength of the soils, of course, the applied load, and the pile diameter, pile geometry, diameter and length. To determine the necessary length of these piles, an engineer, civil engineer, needs a good understanding of soil-pile interaction, good judgment, and of course experience. How can we install these piles? Most piles are driven into the ground by means of hammers or vibratory drivers. Hammers and vibratory drivers. In the driving operation, a cap is attached to the top of the pile. A cushion may be used between pile and the cap. Let me show in the figure. For example, suppose that we are driving by using hammer force. We have to place a cap on the pile to minimize the disturbance or failure on top of the pile. Cushion material generally rubber-like material is placed between cap and the pile and above the cap. In other words, between cap and hammer. The ram may be free-fall ram. In today's technology, it's rarely used. The common varieties are diesel hammers or steam hammers. In steam hammers, they're actually similar to free fall, but the uptake of this hammer supplied with using steam. Steam is taken from intake hole and move this hammer to the top of the cylinder. When this steam or pressurized gas exhausted from the other hole, and this hammer starts to fall. Fall to where? Fall to the top of the pile, creating a free fall energy. The hammer may be double acting hammer. Similarly, intake moves to the top, moves this hammer top, and after the escape of this pressurized gas, the hammer starts to free fall. In the same time, another gas pressure is applied at the top of this hammer, increasing free fall energy. So in this case, the hammer energy includes free fall plus gas pressure, energy due to gas pressure. And the other variety is diesel hammers, similar to steam engines, but the energy comes from explosion of diesel. As we say in the introduction, we can use vibratory drivers. Vibratory driver can be explained in this cross section. Vibratory drivers are simple. In vibratory drivers, actually, we have two electric motor, but at the end we have oscillator to produce a vibration. And this vibration is transferred to the pile. So vibration on the pile eliminates friction between soil and the pile material, so makes driving easy. Let me show figures. The left two figures are from, I think they should be double acting. Yes, this type of hammers, double acting gas hammers or steam hammers. And the right two figures are vibratory hammers. Vibratory hammers attached to the top of the pile. And these two are vibratory motors, oscillation motors. These vibratory drivers are used for pile driving and also sheet pile installation and removal as well. Sheet pile, special kind of pile. From a different point of view, piles may be divided into two categories based on what? Based on the nature of the placement. From this point of view, piles may be displacement piles or non-displacement piles. Driven piles are displacement piles driven by using a hammer or vibratory driver. Anyway, these are displacement piles. Why? Because they move some soil laterally. Hence, there is a tendency for densification of soils surrounding them. Let me show, yes, here. When we drive this pile, whether by using vibratory driver or by hammering, this volume, this pile volume inside the earth, inside the soil, results in a lateral force along the sides and finally results in densification of surrounding soil, resulting displacement of soil. Concrete piles and close-ended piles, pipe piles, steel pipe piles are high displacement piles. However, steel H piles displace less soil laterally during driving. It's easy to understand because close-ended pipe piles or concrete piles have greater volume compared to H-section piles. H-section piles displace less soil, so they are low displacement piles. Board piles, on the other hand, are non-displacement piles. Why? Because their placement causes very little change in the state of stress in the soil. Cast in situ piles are constructed using similar to CFA, yes, similar to CFA piles, but CFA piles are spatial case. It should be continuous. The auger should be continuous in the equal length with pile. It's not necessary. In general, cast into situ pile starts with making a hole and then cage style reinforcement and concreting. So This method consists of three primary phases: lowering, cage lowering, reinforcement lowering, and concreting. Let me show in the picture. Yes, this is cage reinforcement. The worker lower this cage inside the hole, dig before this, of course, and the soil materials taken to the surface, so very little volume change or no displacement is observed during this construction of these piles. So after an introduction or definition and also classification of pile foundation, let us talk about calculation of pile capacity. The ultimate carrying capacity, load carrying capacity, Q sub U of a pile, is given by the equation you know from the previous section. Point bearing and shaft bearing or skin friction. The ultimate resistance per unit area developed at the pile tip is Q sub P. Of course, Q sub B should depend on soil properties. Similar to shallow foundations, first of all, we have to model failure around the tip of the pile foundation. Again, similar to shallow foundation, under the pile foundation, a triangle-shaped active zone develops. Inside this triangular zone, the soil material doesn't fail. And this triangle mobilizes through the bottom with pile tip, and along these two sides, soil starts to fail. Another failure surfaces are these two curves and the almost vertical, these two zones. And from these two triangles, stress is transferred to the soil mass. So using this model and just taking force equilibrium, we can get an equation, maximum capacity equation. Here, Q sub P should depend on soil properties, soil strength properties. What are the soil strength properties? Soil may have cohesion and internal friction angle. Cohesion symbolized by C and multiplied by a factor. We use star here because NC factor is modified for piles. The second term is Q and Q. This Q comes from surcharge or soil stress at the layer of at the depth of foundation of here. It means length of the pile foundation. And the third term, gamma term, gamma is unit weight of soil multiplied by d and gamma. But I have to say this third portion may be cancelled. Why? Because the width or diameter of a pile is relatively small compared to length. It's around 30 centimeters to 90 centimeters generally. But length maybe 10, 15, 13 anyway, meter. And this term may be cancelled or maybe dropped. And our final Q sub P equation simplifies to C and C plus Q and Q. These values, these n coefficients, n sub C and Q and gamma, these are modified factors for piles. Note that the term Q here has been replaced by Q prime. When we put prime here, the point bearing of pile can be represented by this equation. QP, Q sub P, we just calculated using this equation, multiplied by area, base area of pile tip, stress multiplied by area. Now this is load. This is point bearing capacity of a pile. So let us put Q sub P equation here. This is our point bearing capacity. What about frictional capacity? For end bearing capacity, we use soil property of one single soil. Why? Because at any depth, this area is supported by one single soil unit. So we can use one single soil property, cohesion and internal friction dependent N factors. These N factors, as you know, depends on internal friction angle. But when we calculate skin resistance or shaft resistance along the pile length, soil may be actually in general layered. Soil is layered. So we have to consider all these soil properties of all these layers. For example, in this figure, 3 layers are shown, but it may be 5 layers, 10 layers anyway. So our shaft resistance will be the cumulative of perimeter multiplied by layer thickness. What does it mean? Side area of pile. In other words, area of pile-soil interface. When multiplied by F, unit friction resistance at any depth, unit friction for this soil, for example, or unit friction for any soil, when multiplied and when taken cumulative, the result is total shaft resistance or skin resistance. And total capacity, Q ultimate, is the summation of Q sub P and Q sub S, the summation of these two. Okay. Is there any question, dear friends? Is there any question you can ask? If not, I'm gonna stop here and we will continue next week. Okay? I think there's no question, so I'm stopping here. See you next week.